Hi. Okay. I'm Cook, JPL. I'm the PDM for the Aircraft Technology Center, which includes some operation stuff, testbeds, and the ground software. Um, so it gets a lot of acronyms after my title. So I, is that, okay. So I be a little pedantic about labeling everything because I try and keep everything straight. So like I try and make sure everything's, when I say software, flight software, I say instrument flight software because I talk to the spacecraft people and have their own flight software. But acronyms here. So basically, basic breakdown. There's not too much B&B here. This is our B&B structure that Matt Smith manages out just engineering area, but we're talking mostly about functional requirements, which mostly goes into the flight software. I guess all the same processes were used to track the instrument ground software requirements that went into Skittle. And I guess Kylie already showed you this breakdown. We did a very nice job of capturing everything in these FDDs, putting up the requirements and describing them and breaking it down into these areas. There's also, I probably should include, there's another ground software, some ground software requirements, some of which come from the ground system side rather than system or ground segment, flight segment. You have a lot of interfaces with the Skittle into the roaming ground system. Part of the instrument is delivered to SSC and they run our code. So we have all this breakdown of requirements, level 4, instrument flight software, level 5, instrument ground software requirements. We had a very formal process with lab testing, all out and tied back to these FTTs, which has quite help. There's lots of aspects to this. Let's start here. Have the functional test bed. There's people talk about test beds. This is the functional test bed. Basically, doesn't have optics in it. You have limited amounts of optics for images in the camera. We used it was kind of built up out of the engineering development units that our electronics or avionics people built. They built those units. This is the hardware to show that the form, fit, and function work, and that they can characterize those units and develop the testing for the flight units that came later. Those units basically look like flight units, but you can't fly them. They don't have vacuum or temperature or thermal compatibility, but they do function very much like flight hardware. And we actually have very good luck with that. Just about everything that went wrong, every quirk we found on the flight instrument or ahead of time, early flight software testing, something that the instrument was going to be doing. There's a lot of fidelity in our test bed, that software interface level. Okay, I guess I will mention testbed was run sort of part of INT, run very much like an INT activity. We had shifts, we had shift requests, and daily meetings like ASIA did. INT started earlier, and that was key to getting everything going. I mean, there was often a big push to a flight software release, and there would be 4 weeks of testing. Pay that out and make sure everyone showed up and got the work done. As you can see, we got lots of requirements that were verified, flight software and ground software. Okay. And this is the summary here. This is the flight segment side, level 3 requirements that were levied on CGI. And the status at the very end here. Left ones here that have I didn't want to throw a lot on your coming. Sure. Thanks. Ground segment and more work to be done on the ground segment ground segment schedule laid out here. So the stuff we're doing after delivery, a lot of this is related to data reduction pipeline, so handling the science data. Okay, I go to the next chart here. Okay, so the way this came together is FTB was added at CDR. It was built out of the existing EDU hardware that came from avionics that didn't have a future per se. It wasn't meant to be or planned to be integrated together, but we used those EDUs. And we also worked, and part of that is electrical ground support equipment, standard JPL term for all the non-flight hardware, electronics, software that goes into testing on your plane. Realized early on is that we couldn't run a test bed without actually building up all systems to command data and systems which is working with supply systems, making this that we could do testing. So we took over this ground GSE equipment and went on to create all the hardware. Also, we were able to take the SIS spacecraft interface simulator from Goddard and some other development racks. We developed, I think we got 3 systems that could be used to run test beds or the instrument, all interchangeable. Extra hardware is very useful. Mix and match and keep test beds going, CGI running. We can test on 2 test beds and CGI at the same time. Scope. And TB1 is the largest complete. TB2 is used both directly by the flight software development people and also by the testbed people for doing some verifications. Very useful to have 2 systems. I did debug all the PAM software, which was quite complicated. A few months to be able to run 2 testbeds at the same time. We also provided a venue for running basically our GITL code in JPL to support INT. That certainly serves the purpose of testing the GITL code, but also when we went to feedback and we're actually doing ground and loop operations, we had a place to run it, process the data. We also provided the venue for running pieces of code that SSC provided. So all that fell into the testbed area. So fill in anything that was missing. Post-delivery, we are going to continue to support flight software and FSTOL testing. That's FSTOL is the scripting language that's used on the spacecraft at SSC on the part of that validation process. We also have the visit files, rest rehearsals, and anomaly resolution support. Operators, etc. Okay. We also are going to, as things have moved here, I mean, at first, whatever hardware was available, we incorporated. And as things have progressed, we're going to, a simulation of the spacecraft software is going to support us in installing that in our systems. Continue to improve support operations and home and INT better. We're also going to get cameras so and get 2 cameras, which is often to have 1 out of 2 cameras. That's been a limitation. And already you can see the acronyms up here. See, that's a measure of complexity of CGI. And it will now get worse. This is maybe, I don't know if someone has presented a diagram of this yet. This is the ground segment, flight segment. This is our ground software running at SSC. This is our flight software running on board. This is the WPC. This is our processor. That's the simplest version of our testbed, is just running this processor. There is hardware out here. Some of this is like COTS hardware, as Heidi mentioned, like the cameras that lead to complexity in their interfaces. Each of these pieces of hardware has an interface slice or component, then talks to the like software here. So this is also, you can see the same breakdown in requirements down. So for instance, we got flow control, which controls the optical bench and stuff. And this is camera, the fast steering mirror, FPGA stuff, this one here, XCAMs and DMs. So let's see, so I guess we should. So this is how we test CGI, which is a complete flight hardware here. We have the Goddard-provided SIS space simulator that runs Assist, which is the system that's going to be used in operations, and we provide a simulation of the environment at SSC that runs our ground software. So this is an arrangement with a lot of glue code and other things that makes this all work. So we recycles as alpha skittle during TVAC or ground software. The test bed doesn't have optics. It doesn't have thermal except one plate with 6 heaters on it. And a single camera. We have a projector where we turn the camera for 2 out of 6 PAMs. Actually, even more complicated than that, but we do have the ability to plug 2 PAMs into any 2 slots. Software does it. That one. We're going to be improving that simulation, the spacecraft flight software simulation. We're going to be adding another detector, so we have a second camera. Vacuum chamber. I guess we only had one DM electronics at first, but we actually, this is the story, we actually scavenged the prototype and made a second one, so we had something to flight software. This more fish, different level. I think we're back to March. Like these are just down to a nice table, and we had room for a thermal plate for thermal testing, projector, and a camera just sitting here in the back. Projector. It's a cell phone, the right kind of cell phone, and some optics that feeds into the camera head and the proxy electronics. And this is our testbed 2, which we put in the other side of the room, so we can have 2 teams working at the same time and talk and not overhear each other. It's that kind of confusing. Okay, and then I guess this is like early on, we just had the processor board and power system, ICE. CTCE, the thermal control system, played for some, and it's developed into this. I have great pictures for. I have a label picture, and we are going to be creating a proxy electronics. It's a prototype that we got, and making up a camera and actually, which I guess that's 25. Yeah, this is the label version. I guess. Resolution, but like this, for instance, this is what a DME looks like. This is a full functioning DME. Other DME over here, which is basically just enough cards on the back plane, not mounted, that gives enough interface that the flight software has to talk to, etc. Okay, so I guess to wrap this up, like we'll talk. Some of this. There is a concept in JPL called the system testbed, which is where flight hardware comes together with flight software for the first time. Basically, where the testbed started. But it also became this venue for testing all of those electronic reviews to make sure they talk to each other about the quirkiness of the COTS hardware, issues with FPGAs that we designed ourselves. That was get worked out. And there was saw issues with the camera grounding early on. Testbed was a venue where you can actually change a lot of things easily. It wasn't structured as flight, but we have good configuration management. That's important. But it's more fluid. Certainly when we tested software, for instance, I guess there's sort of the spiraling up of lower level testing with Testbed 2 to formal testing with Testbed 1. That was very useful to have levels of attack. You can be more responsive and then be more formal. I will point out that as well as adding the EQ hardware, we also had other configurations. We did have the projector, so we could keep the camera. We had Vaughn talked to this before. We had a line of sight configuration test where we actually moved fast steering mirror with the camera, optical input, jitter, and everything, so that we did that with the test bed special configuration for a few months. That really got that locus characterization done early. We also did a thermal control test where we control the plate. Showed that the software algorithms very well. Actually, I think I did that early on, and that was a turn. Urgent behavior, that's key here. Any complex system, especially when you bring all these parts together, I think we were able to find so many things ahead of time. I mean, I guess like Gassi had mentioned before, where we had the problem with resistors, shifted out 6 months. Testbed was still there to working on issues, even resistor issues were taken care of. There's still there's complexity in the optics and in the electronics, but there's separately parallel. And multiple things, so we have levels of tests. That was important. Making sure people had jumped away after the company. I think developing the EGSE ahead of time and bringing it out, exercising it, training people on it. So we went into TVAC or SBT, actually running the flight instrument. It's just sort of there, robust. We weren't solving problems about losing data while trying to fix the instrument. And I also, and post delivery, we're going to be continue to maintain it, develop it. It will be the one thing left here on Earth, in Pasadena on Earth, whenever all is said and done. If you want to know what's going on, let's go back to the test bed. There have been many times when something would happen, and the first thing you do is like, oh, why didn't you see that at the test bed? Go back to the test bed and tweak it around and size find that. As soon as you do that, you can sort of stop playing with the flight hardware and you can go to the test bed and solve the issue. That's where sort of thing really helps. This is our configuration management. I think we are up to, every time we move to cable, we change this diagram. At least 200 different versions. Thank you.
Any questions for Tim?
One on the chat.
Yes, I should.
Oh, question in the chat for time.
Okay, well, we'll put that up at the deadlocks in flight is the question.
Oh.
Any other questions? Yes.
So if you send a DM command to the DM electronics on the functional bed, like, does it actually receive that? Like, you like send a command to it?
Yes, I'm going to say yes. The thing is, that's right. There's no feedback like command to the DM electronics. You set a voltage on pixel, but there's not a feedback. So it's all about sending commands, and there's some handshake that says that it's receiving. Have it like an independent tag, got a voltmeter. EME we have actually was used to power DMs. It has all the functionality. The other DM we have, very prototype, that one just has the like power board, and the interface board that's enough to see the settings, but it doesn't do anything.
Does it go through like the voltage checks and things like that when it like sends it?
It does the same handshaking with the flight software, so it's representative, so it's the same timing and stuff.
Yeah.
As far as like behavior and buses and flight software, doesn't actually.
Yeah, but if you sent one to it and it didn't error out, then you would be confident that if you sent like a similar thing to the flight software, that it would be safe.